Let's talk about the Gauss-Jordan method to solve linear systems. First of all, a couple of definitions. Row echelon form. Remember, this means that all rows consisting entirely of zeros are at the bottom. The first non-zero entry in each row is a 1. We call that a leading one. And every leading one appears to the right of the leading ones in the preceding rows. So here's some examples. Okay, that's in row echelon form. Notice the leading ones marching downward in a stair-step manner. Here's another example. And hang on, let me fix this a little bit. That's better. Okay, and notice here we have the leading one. We have a leading one in the first column. We do not have a leading one in the second column, but we do have a leading one in the third that comes from the second row. Okay, so this first one we have zeros below it. This leading one has zeros below it. And here's some other ones. There's several other ones here, but those are not leading ones. In other words, right here and right here, these are not leading ones, so they do not need to have zeros below them. And neither of these examples had any zero rows, but if there were any, they would need to be at the very bottom. Okay, let's talk about reduced row echelon form. So it's got to be in row echelon form above, but there's an extra qualification. Each column that contains a leading one has to have zeros everywhere else in that column. So here's some examples that are in reduced row echelon form. Okay, this example has a zero row at the bottom. Notice my leading ones have zeros everywhere else in the column, not only below, but also above. Here's another one. Okay, look for your leading ones. Here's a leading one, here's a leading one, and here's a leading one. Notice each of those leading ones has zeros everywhere else in the column, both above and below. When we were in row echelon form rather than reduced row echelon form, where are our leading ones? Here, here, and here. Here the leading ones have to have zeros below them, but not above. Now let's talk about Gauss-Jordan elimination. What we're going to do is use row operations to transform an augmented matrix into an equivalent matrix that's in reduced row echelon form. When we did Gaussian elimination with back substitution, we put it in row echelon form. Now we want it in reduced row echelon form. Let's look at this example. Here's what we want it to eventually look like. Okay, so we start by writing our augmented matrix. That's 2x1 plus x2, sorry. Okay, so we approach this in the same way that we did when we transformed it into row echelon form. In each column, what we're going to do is get the 1 first and then the zeros. Exactly like what we did before, we just are going to have a few more zeros than we did previously. So the first thing that we want to do is we want to make this into a 1. And to do that, we are going to multiply that row by the reciprocal, since there's not any convenient row to switch it with that'll give us a 1. And so here we get 1, and then 1/2, and then 7/2. Second row is still here. Now we want to get a 0 in this column right here. And so to do that, we are going to take the opposite of that number, which is -3. We're going to multiply by the row with the 1, which is row 1, add to the row we're working with, and back into that same row. So the first row remains unchanged. Second row, I'm going to skip the scratch work. You should get 0, and then 1/2, and then 3/2. Now what do we want to do? Now we need to get the 1 in the next column. We want this to be a 1. So we are going to multiply that second row by 2. So that'll give me 0, 1, 3 in my second row. First row still the same. So right now we have it in row echelon form. If we were going to do Gaussian elimination with back substitution, we would be through with our row operations, but we want to get it into reduced row echelon form. So we want to get this into a 0. The way we get a 0 in that location is we take the opposite of the number that is there. So that'll be -1/2. Multiply that by the row that has the leading 1, which is row 2. By leading 1, I mean that's the one that we put there that we deliberately changed into a 1. So we're going to get -1/2, row 2. Then we're going to add the row we're working with and put it back into that same row. When we do that, we should get 1, 0, 2 for our top row. Our second row is still 0, 1, 3. Let's put the vertical line back in. And now, do you see how easy it is to read the solution off of this? x1 is 2, because, let me write out one more step. (1x1 plus 0x2 equals 2). That's my first row, and so that tells me that x1 is 2. And similarly, x2 is 3. So our ordered pair solution is x1, x2 is equal to 2, 3. And don't forget to check your answer. All you have to do is plug those numbers back into the original equation, and you'll see that it works. Let's do another one. Here we have a 3 by 3. We have 3 variables and 3 equations. First, check that all your equations have the constants on the right-hand side. Ours do, but I need to fix a couple of my equal signs. I think everything else looks okay. Also, make sure your variables are in a consistent order. And then write your augmented matrix. Let me write down what we're looking for. We want to get we want to make ours look like this, and then we'll be able to read the solutions right off of our final matrix. So here we have 0, 3, negative 1. There's my vertical line, and then negative 1, 1, 5, negative 1, negative 4, and then our last row. And hang on, let me change this into a plus. Sorry, my usual problem with this program not liking a few of my mathematical symbols. So we are going to make this a plus 2 in that third row. Okay, let's do our first row operation. What do we want to do? We want to get a 1 in this very first slot. Okay, how's the easiest way to do that? Now, you can't multiply through by the reciprocal of that 0 because 0 does not have a reciprocal. So if you've got a 0 there and you need a 1, what you have to do is switch rows. If you can't do that, then there's not anything further that you can do. So that's what I want to do. We're going to switch row 1 and row 2. I chose row 2 because row 2 already had a very convenient 1. But if I didn't have a 1 in either of the slots, as long as I had something that was non-zero, I could still switch it and then change it into a 1 in the usual way. So here, so there's the matrix that I get when I do that row swap. Now what do we want to do? Now we want to get zeros here and here. And one of them we already have a 0. So we just have to worry about that third row. So to get that third row, to get that 3 into a 0, I'm going to take its opposite, multiply by the row with the leading 1 that we put there. So that'll be row 1. Add the third row, since that's the one we're working with, and put it back into the third row. So my first row stays the same. And my third row, when I do the row operation, again I'm skipping the scratch work, but I will get 0, 21, negative 1, negative 1. And that should be a negative 4. Slightly illegible there, sorry. Okay, now we need to move to the second column. Our first column is done. Don't start on the second column until you've got the first column completely right. That way you won't undo work that you've previously accomplished. So we want to get this into a 1. So as usual, we will multiply that row by the reciprocal. So that'll be 1/3 times row 2. Okay, now we need to get zeros here and here. So we are going to take the opposite of those numbers. So negative 5. Now we're going to take that negative 5, multiply it by the row with the leading 1, which will be row 2. We're going to add to row 1 and then back into row 1. And on the third row, we're going to take the opposite, so negative 21, row with the leading 1, plus the row we're working with, row 3, and then back into row 3. Make sure you're doing the row operations yourself so that you can verify that you know how to do them correctly. So our first row should turn out to be 1, 0, 2/3, and then negative 7/3. Second row remains unchanged. Third row will get 0, 0, 6, 6. So now we need to get a 1 here. Our second column is finished, so we move to the third. So we want to get a 1 here. You always want to get the 1 first and then the zeros. So we are going to multiply our third row by the reciprocal of that 6, so 1/6. So that gives me 0, 0, 1, 1 for my third row. My first two stay the same. Now we want to get zeros elsewhere in that column, so we want to get this and this to be a 0. So we're going to take their opposites, so that looks like -2/3 multiplied by the row with the leading 1, which will be row 3, and then add to the row you're working with. When we do -2/3, row 3 plus row 1, we should get 1, 0, 0, -3. Now we want to do the second row, so take the opposite of that number. Take the opposite of the -1/3, that'll give me +1/3, multiplied by the row with the leading 1, and then add our row, and then back into our same row. This will give me 0, 1, 0, 0, and then my last row is 0, 0, 1, 1. It stays the same. What were our original variables? X, Y, and Z. So X, Y, Z, we call this an ordered triple, is going to be equal to -3, 0, 1. Remembering that each row represents an equation.